Okay, let's look at some examples from the 4.1 homework. Some examples of anti-differentiation. So here we have, I'm going to start with number 9, and here we are finding the antiderivative of this pretty complex function here. A lot of stuff going on. But if we think about some of our antiderivative rules, we can notice that, I've got some terms that are separated by addition and subtraction, meaning that I can just focus on the antiderivative of each of these individual functions. I can focus on them separately. And as soon as we split it up, we can see how some of these are pretty straightforward. This is just using the power rule on the x to the 4th function, and same with this. This is just using the power rule for x to the negative 3/2. Remember, power rule for derivatives works for negative exponents and it works for fraction exponents. So the same is true for the antiderivative rule. This antiderivative gives me 1/5 x to the 5th power. And then, of course, I need a little plus c. But since there's 3 different antiderivatives that I'm going to be finding, I'm going to put a little plus c1. I'm going to skip that middle one for now and go to the other one. Okay, x to the negative 3/2. When I use that antiderivative rule, I get 1 over, negative 3/2 plus 1 gives me actually negative 1/2. So I get 1 over negative 1/2 x to the negative 1/2. And then I'm going to put a little plus c3 because that's my third antiderivative. Well, take a look at that middle function. This function has a constant in front of it, right? I've got the square root of x function, but then I also have this 15 over 2 right here. That counts as a constant multiple, and like we learned in our antiderivative rules, this doesn't complicate my derivative, or my antiderivative. I can pull it out in front of my antiderivative symbol, meaning I can just focus on the antiderivative of the square root of x and then multiply by the 15 over 2. But what's the antiderivative of square root of x? I didn't talk about root functions with my antiderivative rules. Well, remember that a root function is really just a power function with a fraction exponent. So all I need to do is just switch that in terms of a power function, and then I can use my power rule for antiderivatives. And I get 1 over, 1/2 plus 1 gives me 1 1/2, or 3/2. So 1 over 3/2 x to the 3/2 plus c2. And then plus, I'm going to simplify this a little bit. That negative 1/2 in the denominator makes this a minus, and it ends up 1 over 1/2 ends up just equaling 2. Now what? Well, there's a few more things that I can simplify, right? 15 over 2 times 1 over 3/2. 1 over 3/2 is just equal to 2/3, right? I can flip and multiply, and I just get 2/3. But what do I do about all these constants of integrations? I have a separate c for each of my individual antiderivatives that I found. Well, stay with me here. I'm going to rewrite this and just put all those constants at the very end. 15 over 2 times 2 over 3, I actually get just 5. So minus 5x to the 3/2 minus 2x to the negative 1/2. And then I'm putting all of these constants right here next to each other. What happens when I add constants together? I get more constants. And if these are all just arbitrary constants anyway, I don't know what these values are. It doesn't matter what the value of these are. If I add 3 arbitrary constants together, I end up with an arbitrary constant. So I can merge all these together into a single plus c. And that's what it'll expect when you actually put this in. I don't need 3 separate constants for each of my antiderivatives. I can just combine them all into one arbitrary constant. And then that's my answer. How can we check our answer? How can we make sure what we did was correct? Let's say we're on a test and we don't get multiple chances to get this correct. Well, I can check my answer by just going the opposite direction. What happens when I take the derivative? If it's correct, I should end up with what I started with. So let's take the derivative real quick. My derivative of 1/5 x to the 5th, I'm going to get 1/5 times 5, which is just 1. x2, I'll subtract 1 from the exponent, and I get 1x to the 4th. Minus my next term, I'm going to bring down the 3/2, and I'll do 5 times 3/2 x to the 1/2. I subtract 1 from the exponent. And then my last term, I get minus 2 times negative 1/2 x, and then I subtract 1 from the exponent, giving me negative 3 halves. What's my derivative of plus c? I just get 0 because it's a constant. If I simplify this, I get x to the 4th minus 15 halves x to the 1 half, or how can I rewrite x to the 1 half? Just as the square root of x. Minus 2 times negative 1 half, actually the negatives cancel out, and I'm left with just plus 1, so plus x to the negative 3 halves. Does that match what my starting function was? It does. And so, therefore, we can be very confident that we got the answer correct. Okay, let's look at the next problem. Okay, next I want to look at number 5. Very similar, just another antiderivative that it's asking me to find, but slightly different things that we're looking at here. Once again, I can split this up into 2 different antiderivatives because I have this addition in between. And both of these have a constant in the numerator. That counts as a constant multiple, which means I can pull those constants out. But the reason I wanted to talk about this one is even though each of these pieces look similar, they're fundamentally different. Why? Because hopefully you recognize this as our special case where we're not actually using the power rule to find that antiderivative. My power is -1, meaning this has a different antiderivative rule. What's my antiderivative of 1 over x? It's natural log of x. Notice I'm not going to put a plus c because I can just wait and put a plus c at the very end. My other term, I can rewrite that 1 over x to the 5th as x to the -5th, right? If I have a power in the denominator, I can switch it to the numerator and just give it a negative exponent. And now I can use the power rule. So I get 4 times 1 over -5 plus 1 times x to the -5 plus 1. And now that I'm done, now I'll put the plus c. So let me simplify that second piece. I get -5 plus 1 is -4, so I get 4 over -4, x to the -4 plus c. And of course, 4 over -4 is just -1. And there's my antiderivative. So the reason I wanted to go over this one is just to make sure you recognize that when you see 1 over x, you're not using power rule. That's your special case where it just becomes the natural log of x. But if you see 1 over x to a power, then you can switch it to a negative exponent and then just use the power rule like normal. The last example we're going to look at from the homework is number 16, and this is our applied problem. We've got a ball being thrown upwards, and so we're going to be dealing with position, velocity, those kind of things. But now we're going to be looking at it through the lens of antiderivatives. So you'll notice what's given to us. What's given to us is the velocity function, 96 minus 32t. And the first thing it asked me to do is, let's find the position function. Well, from what we learned about in our concept video, because velocity is the derivative of position, position is the antiderivative of velocity. So that's what I'm going to do, is I'm just going to find the antiderivative of my velocity function. The antiderivative of this 96 minus 32t. Well, using my antiderivative rules, I can split this up into 2 different antiderivatives. The 96 is just a constant, so that just becomes 96t as my antiderivative. Minus, and then my antiderivative of 32t, remember I can always put a little 1 here as my assumed exponent, and then use the power rule. And so I get 32 over 2t squared. And then of course I'm going to have this plus my arbitrary constant. So if I simplify that, 96t minus 16t squared plus, well, this is actually one of those cases where I can actually solve for what this constant is. Remember that plus c is there is because I can put any constant I want there and it still counts as an antiderivative, but in some cases we have a specific constant that needs to go there. In this problem, we can actually figure that out using this piece of information. What does this problem tell me first? It tells me the ball is thrown upwards from my height of 256 feet. This represents my initial height or my initial position. A mathematics way of thinking of this is S of 0 is equal to 256, right? My position at time 0 is equal to 256 feet. So what that represents is that's a data point. And I can use that data to solve for what that c value needs to be. We've already decided that this is my position function. If I plug in 0 to this function, I should get out 256. Using that, I can solve for what c is. What's 96 times 0? Well, that's just 0. 16 times 0 squared, that's also 0. And so I'm just left with c is equal to 256. And therefore, I can now write a very specific position function that does not have an arbitrary constant, that has a set constant. But that's part A. I'm done. There's my position function for where the ball is at any point in time. So let's move on to part B. Part B asks the question, how long would the ball take to reach the ground? Well, if I read that problem carefully, hopefully you should be able to figure out what it's actually asking for. This is asking for a time value because it's asking the question, how long? So, how much time will it take before the ball reaches the ground? Well, if the ball is reaching the ground, what do we know about its position? We know the position is 0. 0 represents the ground, right? Any positive number represents being above the ground, and so 0 represents the ground. So what we're looking for is, where is my position function equal to 0? Notice how that's very different. This is very different than plugging in 0 for t. This is the opposite. I'm plugging 0 in for my output. So let's try this out. Where is 96t minus 16t squared plus 256 equal to 0? Let me reorder this a little bit, and we're going to see how, in order to solve this, I actually just need to factor. Because I'm working with a quadratic equation, an equation that has a power of 2. So I'm going to need to factor this. Well, before I think about factoring it, it turns out that every single one of these numbers is divisible by 16. So I'm actually going to divide everything by negative 16. Why negative 16? Because I want a positive t squared term. If I divide one side by negative 16, I do have to divide the other side by negative 16. But what's 0 divided by negative 16? You just get 0. On this side, negative 16 divided by negative 16 just gives me 1t squared, or just t squared. 96 divided by 16 actually just gives me minus 6, a negative 6t. And 256 divided by negative 16 is actually negative 16, or we can write minus 16. That's much easier to factor. So I can come back and split this up into two different terms, and I get t minus 8 and t plus 2. You can check my math, kind of multiply those back together again, and you see that negative 8 times 2 gives you the negative 16, and negative 8 plus 2 gives you the negative 6. Well, like all quadratic equations, this actually has two solutions. If I solve each of these, I get the solutions t equals 8 and t equals negative 2. So which solution do I use? Well, hopefully you can kind of quickly realize that we are not going to use that negative solution. Why? Because negative time doesn't make sense. So instead, we're going to use that solution. It takes 8 seconds before the position is equal to 0, before the ball hits the ground. Okay, last, part C. Part C is asking, how high will the ball go? Well, this is an interesting question because this is asking, what's my maximum position, right? What's my maximum height? How big will S get? If you think about my ball that's being thrown upwards, at this height of 256 feet, it's eventually going to reach this apex and then come down to the ground, where it's going to take 8 seconds before it actually hits the ground. So how high is that point? Well, the way we're going to figure this out is we're actually going to use our velocity equation. Remember, that was 96 minus 32t. Why are we using my velocity equation? Well, tell me about the velocity during this stretch. As the ball is thrown upwards initially, it has a positive velocity because it's going higher. It's going up into the air. But eventually, gravity has enough of an effect on it that it stops and eventually starts going down. Throughout this section, what's true about the velocity? After it reaches its peak, the velocity is now negative because it's going downwards. It's going towards the ground instead of away from the ground. So this represents a positive velocity, and this represents a negative velocity. So tell me about what's happening right at the peak. What's true about the velocity? Right here, I have a velocity of 0. And that makes sense. This all goes back to what you learned about in chapter 2. Where do my functions have their peaks, their minimums, or their maximums? Where the derivative is 0. And remember, velocity is the derivative of position. So we're looking for where the derivative is equal to 0. In other words, where the velocity is equal to 0. This one's just a linear function, so I can just solve it algebraically. I'll add 32t to both sides. I get 96 is equal to 32t. Divide by 32, and I get t is equal to 3. That's not quite my answer, because this is just telling me when it'll happen, right? The ball will reach its highest point after 3 seconds. So now I have to go back and ask, okay, well, what's the height at that point? And so for that, I have to go back to my position equation. But now I have a specific t value to plug in. I'm going to plug in 3. So I get 96 times 3 minus 16 times 3 squared plus 256. And then I can solve from there. And I end up getting 400. So that's my maximum height of my ball when it reaches the very peak. And then after that, it just falls down until it eventually hits the ground. Okay, but that takes care of number 16. So hopefully that helps you make sense of some of these more complicated problems. But please let me know if you still have questions or if you need any other help on this assignment. Good luck, and I'll see you in 4.2.